presentation is by Tom Golecki. Tom is with Intelligent Infrastructure Systems Group of Pannoni Associates. He's a structural engineer with more than 10 years of experience in the analysis and design of complex bridges. Tom is a real advocate for using program tools to improve efficiency and to make calculations traceable, repeatable, checkable, and highly automated. And recently he's been working on load testing and load rating of complex bridges for legal and permit evaluations. Tom's presentation is entitled Automating Refined Load Rating for Girder Bridges. So I'll turn it over to you, Tom.
All right, thank you. So today I'm going to be discussing my work in refined load ratings, and specifically what I see as an improvement to the standard workflow through the use of automation. This presentation is based on a presentation I gave at TRB, but with some additional time, I'll go into a little bit more detail here. And I also just want to acknowledge my my co-author, Jeff Widener, who's currently at the University of Texas at El Paso. So first, a quick load rating background. We could think of a bridge rating factor as a measure of safety of a bridge for a specific loading. And the general guidance for that analysis is to start as simple as possible with an approximate analysis, so a single line girder approach. And if a single line rating factor is greater than 1, your bridge has an adequate level of safety and no additional work is required. But if your rating factor is less than 1, the engineer or the owner are really left with a decision to make. The bridge could be posted, essentially reducing the live load demand. The configuration of the structure could change, like you could reduce the number of lanes to, again, try to reduce the live load demand. You could rehabilitate or strengthen the bridge to try to improve capacity. You could do material testing to try to better understand the capacity. Or you could do a refined analysis, which I think is really the most logical next step. And that's aimed at better understanding your demands. So a refined analysis typically gives a lower estimate of live load than a single line approximate analysis. And I think it's worth noting here that not all bridges are even candidates for approximate analyses. Because they require a distribution factor from an AASHTO table, that table is only applicable to certain bridge configurations. So it's a function of your cross-section and the some other parameters of each bridge. So things like a variable deck width or different girder stiffness or curvature can kind of bump you out of the approximate analysis routine and kind of force you to do a more refined analysis. So I wanted to get into the differences between an approximate and a refined analysis. So in each approach, your rating factor equation is the same: capacity minus dead load divided by live load, where the capacity minus dead load, you can kind of think of it as a reserve capacity, or what's left to resist live load. And in each method, approximate and refined, the capacity is the same. It's your code-based capacities for various limit states based on the material properties and the configuration. In an approximate analysis, your dead load is really just engineering judgment. A decision has to be made about the self-weight of various components and which members it applies to. And your live load is the AASHTO distribution factor multiplied by the vehicle-induced loading. So in a refined analysis, those two demands are what's different. In a refined analysis, the demands are based on a structural analysis that takes into account the actual configuration and the actual stiffness of the members. And there's a lot of different analysis approaches that qualify as a refined analysis, but for our purposes here, I'm really just going to be talking about finite element analyses, so FEA. So let's talk about the workflow of a refined analysis. You have a structure, a bridge. You probably have an inspection report and hopefully a drawing set to go along with this bridge. And you need a refined analysis, so a analysis model, FEA model, and a set of results. This bridge I'm using as a demonstration here it's a multi-span viaduct type structure, and I'm not sure if you can see from the picture, but it's a 3-girder bridge, and the center girder is a different depth than the exterior two. So an approximate analysis isn't a viable option for this bridge. So generally, the workflow here is to understand your structure and make some decisions about how you want to build the model. Then sit down in front of an FEA program and click through the user interface to build the model, to run the analyses, and to extract the results that you need. And in my experience, that process has been a little bit tedious, it can be error prone, and it's difficult to reproduce, but it doesn't have to be. And that's the automation I want to focus on here, is basically improving that workflow. So we could look at the steps of a refined analysis, and I see it as three kind of obvious steps. There's building the model, analyzing the dead load and live load cases, and then extracting member demands. And I'll get to the rating calculations later. But if we want to look at these steps, when you build the model, it's really conceptualizing the structure, understanding the load paths, and then making a decision about how you're going to represent those elements in the model, deciding on element type, connectivity, mesh size, how you're going to represent a wearing surface or curbs or barriers, how you're going to apply vehicle load, that sort of thing. Once those decisions are made, then you could interact with the defined element program to build the model. Then you submit the analysis, basically let the computer churn and pull out the results that you need. But in this process, what I really want to focus on here are the decisions. So if I look at just what I'll call the engineering input, the decisions that need to be made, they're all up front. Your conceptualization of the structure, your decision about element types to use, mesh size, how to connect things, how to apply loading, they could all be made right at the beginning of the process. And that kind of condenses the engineering effort. So once those decisions are made, they could be documented and kind of passed off as a set of instructions into an automation routine that then carries out the rest of the process, which is really just implementation. And that's the automation I want to discuss. So this flowchart kind of shows how I conceptualize that automation routine. So starting at the top, we basically have our known bridge documentation, and we make a couple of engineering judgment decisions that define our conceptualization of the structure. So then we have basically two categories of information. You have the stiffness and mass information that will go directly into the model, and you have your strength information that is still needed for the rating inputs. So something like your material, like a steel yield strength or an unbraced length, that sort of thing. So all of those inputs then get packaged into one input file and passed into an automated process that, in theory, then just carries out your instructions. So it will build the model, analyze the model, extract results, hand you an output file that's a set of demands. It could even compute ratings internally and spit out your load ratings. So this is kind of the big picture view for what an automation routine could be. But in order to improve on the normal workflow, it doesn't have to be this complex or this comprehensive. Even a small part of this process could be automated, and anything that kind of removes clicking through an interface and replaces that process of interacting with the GUI with a documented and traceable and repeatable procedure is definitely going to be beneficial. So the goal here is really to minimize that clicking through an interface. And software companies, they know this. They're aware of this approach, and they're really making it more easy for their users to do this kind of thing. Whether they call it an API or a macro, there's almost always tools available to give you access to the FEA program's commands without directly needing to manipulate the user interface. So what I want to talk about today is my implementation of an automation approach. And I think the automated process I kind of show on the flowchart there, I group into three chunks. The first is building the model. FEA programs in general are getting very good at helping you to build a model. They either come with like predefined templates or like a guided interface or a modeling wizard. There's tools with these programs to make it easy to build a model. So I'm not really going to focus there. And then the green box where I talk about ratings, the load rating calculations that use your model results, they need to happen whether or not your process is automated. So there's not a huge challenge in automating the actual rating calculations. Where I want to focus on today is automating the analysis and the results extraction. So I think, in my experience, that's where I've seen the most problems and the most time spent manipulating the GUI, the user interface of these programs. So the first thing I'm going to touch upon here is composite member demands. And I think this is a pretty common problem. As soon as a model is refined to the point where you now have multiple elements representing a single component, it becomes more difficult to interpret your results. So if you want a composite girder moment out of a model that modeled that girder with a beam element and then shell elements representing your deck, you really need to consider the moment contribution of the axial force couple between the two, the contribution from the beam element representing the girder, and the contribution from the shell elements representing the deck. And that process is tedious, and to try to do that basically by hand using outputs from each element is time-consuming, and it's difficult, but it really lends itself to automation because it's repeatable. So once a routine has been developed to compute this net section moment, you could repeat it for each load case for each location of interest. And that is a huge improvement on efficiency. So there is a workaround for this specific problem, but it requires a couple of assumptions. If you can assume that the net axial force in this cross-section is 0, and you're okay neglecting the deck element contributions, you could use the girder element, the girder beam element axial force directly multiplied by the distance between the centroids to estimate your moment. But again, it requires a handful of assumptions, and the engineer performing the load rating really needs to be okay with those assumptions in order to use that approach. The next challenge I want to talk about is a choice of a live load solver. So I think there's really two obvious choices for running your live loads, either a quasi-static approach or an influence surface approach. And the quasi-static, you can think of it basically like moving the truck or the vehicle along the bridge in predetermined steps with the goal of putting the vehicle everywhere it could possibly be on the bridge. Once you have each of those individual locations analyzed, you could take the envelope of results, and within that envelope, you'll find the worst case for any location on the bridge. So depending on the size of the structure, this could be a really long analysis time. The alternative here is an influence surface approach, where you choose an output quantity to minimize or maximize, and then solve for the vehicle location that minimizes or maximizes that specific output quantity. So the drawback here is you really need to know ahead of time what your governing location is going to be, or you need to select a lot of potential locations, and again, the number of analysis cases can get very high. But an additional complication here is that when your output quantity that you're choosing to minimize or maximize is something like a composite moment, an FEA program may or may not be able to select a compound output, something that's a function of multiple elements, as the quantity to maximize. So again, either of these approaches really requires some thought, and it's up to the engineer to decide which to use. And the last challenge I want to talk about with analysis here is how to handle construction sequencing. So for a composite multi-girder bridge, the same model, you really want to represent your non-composite dead load, your long-term composite dead load, and the short-term composite live load. And that can be sort of difficult because it's essentially a different stiffness that needs to be represented in each of those cases. So most commercial FEA programs allow you to modify stiffness as a function of some other parameter, either a direct modification or maybe a function of time or temperature. But essentially what you can do is modify your deck stiffness. So in a non-composite case, the deck has no stiffness, and in a long-term composite case, it has a portion of the stiffness. And in the short-term composite or the composite live load case, it has its full stiffness. And what I found is that in addition to that, it's really helpful to represent the dead loads as loads rather than through element densities. So take, for example, a wearing surface. The self-weight or the dead load of your wearing surface requires a different load factor. So you really need to represent that in its own load case. And I think having your loads applied, or your dead loads applied as loads rather than as element densities in multiple load cases really gives you a finer resolution, a finer control over your dead loads. So now that we've gone through a couple of the challenges, what I want to get into are really the benefits. And I think I already mentioned that the benefits of a refined analysis are a more accurate representation of your structure and typically a lower live load. But what I really wanted to focus on here are the benefits of automating the process. So I need to say it's a little bit, the benefits of automation are a little bit dependent on the flexibility of the automation routine. So all of the model images on this slide and all of the model images you see in this presentation were all created with the same automated routine to build a multi-girder model. And there's a bit of a trade-off here between the complexity of the routine and how easy it is to develop. But the more generalized it could be, the more applicable it's going to be. And more bridges will fall into basically the applicant pool, or how many if your program is more general, it'll apply to a lot more structures. So with that said, I think the big benefits of the automation routine are efficiency, transparency, and repeatability. And I want to kind of talk about these a little bit more. First, efficiency. Being able to condense the engineering effort right up front and not have to spend time clicking through an interface to build a model. It's just a better use of the engineer's time. When I say transparency, what I'm really meaning there is the process is traceable. So take, for example, if two engineers are each performing a load rating, a refined load rating, using a manual process where they each sit down and build a model using a GUI, they're going to get different results. And then when they look at each other's results and try to compare, it's not going to be obvious how those two analyses are different. They're going to have to do some digging into element choices, how each member was represented, how they were connected, how dead load was represented, how live load was represented. It's going to be a significant effort to try to compare those two analyses. However, if the same two engineers did a refined load rating using an automated approach, they're probably still going to get different answers. But finding the differences between those two analyses is as simple as comparing their inputs with that set of instructions. And then it becomes immediately obvious, are there differences in engineering judgment? Are there differences in interpretation of the structure? And to me, that information is incredibly valuable. As an engineer, I want to know how my judgment differs from someone else. The other benefit here I want to talk about is repeatability. So let's say once the comparison between the two manual approaches shows that one of the two had an error and needs to be fixed, rerunning that analysis by hand, it could be a substantial undertaking. It could set you back to rebuilding the model, rerunning the analysis, and re-extracting results. But if there's an error found in an automated routine, it's just a process of changing your input file and rerunning the code. And that is a huge jump in efficiency. And because it's now repeatable, it is essentially parametric, meaning that you could change a parameter and run the process and figure out how that one parameter change affected your results with almost no user time. It's all computer analysis time at that point. So effectively what I'm saying is that a routine could be repeated as many times as you'd like to be able to find the sensitivity of your output to maybe an unknown parameter or that sort of thing. And in addition, you could really code best practices into the automation routine. Say something like how you represent a non-composite girder. It's not obvious. But once you've solved that problem, once you have an approach that you're comfortable with, it can be documented in this automation routine, so you don't have to remember how you did it last time when you want to use it again. And also, in terms of self-checking, I think as an engineer, when I do a refined analysis, there's a handful of things I'm going to do every time in terms of self-checking, and I was able to write those into the procedure so that it really saves myself time. So I think the best way to really appreciate the benefits of this automation routine is with a quick example. So up until this point, I've been kind of speaking in generalities. I'm advocating for more refined analysis and for more automation in refined analyses. So from here forward, I'm kind of going to talk about my development, the automated routine that I developed to improve the workflow. And I'm going to do it with a simple example. So in the next 10, 15 minutes or so, I want to go through the first illustrative example from MBE. This is a really simple bridge that has a single line girder rating in MBE. So what I want to do is do a refined analysis of this bridge, and then I can compare. And in the process, we'll be able to see the workflow of using an automated refined routine. So this bridge is a simple structure. It's 4 composite girders and a concrete deck. So I think step 1 is conceptualizing the structure. It's a fairly easy structure to understand, and that kind of makes it easier on us now. But it also saves time in this quick demo. So I'm going to choose to model the deck with shell elements, the girders and diaphragms with beam elements, and I'm going to choose to neglect the curbs and barriers, basically treat those as non-structural mass. So the first step in defining an automated, your set of inputs for an automated routine is locating the origin. And now all of my coordinate inputs are going to be based on this location. So you see the location I selected here, where the x-axis is along the length of the bridge, y-axis is across the width, and z is vertical. And my origin is in the center of the deck, so the z-coordinate of my deck shells will be 0. And the y-coordinate of 0 represents the center line of the bridge. And that allows me to check symmetry on the girder inputs, basically by saying I have the same plus or minus y coordinate. So the first thing I'm going to do here is start defining components. And in the next handful of slides, I'm going to be defining components, and there's going to be a yellow box on the bottom. And I know the text is small in there. The purpose of that box is really to show the amount of input that I need in order to define this component. I don't intend for you to read and understand everything in the box. So take, for example, the deck. I've grouped my deck into 3 different deck regions. So 1 in the middle and 1 under either barrier. And the reason for that is just to assign non-structural mass to the deck regions under the barriers. So that's the only difference between my 3 different deck regions. So you see here, I'm basically just locating the 3 different regions, assigning a thickness and non-structural mass inputs. And then the automation routine will take care of meshing these with shell elements, connecting them to one another. The next component I want to define are girders. So there's 4 girders. Each one has a bottom cover plate. So my input then, I'm treating them as 12 separate girders. So this input syntax is entirely something I made up. And it works for me because it's general. I think you could very easily define the inputs here in a more condensed format, but you do that at the cost of some generality. So I found this format to be really useful to define a wide variety of structures. And I think defining 12 lines of input to define these 4 girders is not that bad. So that's the method I chose here. So here I define my girder components, basically the start and stop locations, the material properties. I locate it vertically by defining a haunch. I define the connection to the deck with a connection property. I'm defining it here as composite, so I'll use a rigid link to connect them. And then I also provide some information needed for the ratings. So unbraced length, whether or not the web has transverse stiffeners, whether or not the web is coped, that sort of thing. So onto the diaphragms, again, the same idea as the girders. I'm identifying components, I'm locating them, I'm giving them a cross-section property designation, and the model will take care of actually putting the elements in these the automation routine will take care of putting these elements in the model and connecting them to the rest of the components. Next is boundary conditions. So here I'm putting a pin and a roller on the end of each girder and designating which degrees of freedom I want to restrain, and the automation routine will take care of actually figuring out which node is there and assigning it to the node. Material properties and cross-section properties, this one is pretty straightforward. It's really just a matter of defining the linear elastic properties of the concrete and the steel. And again, I'm adding in the strength information. That'll get used for the rating calculations, not necessarily in the model. And then finally, loading. So for this example, I'm going to choose to run a quasi-static live load. So I'm locating the locations, the lanes where I want to put the vehicles. And according to MBE, I want to keep a 2-foot spacing between the edge of a curb and the vehicle point loads, and I want to keep a 4-foot spacing between passing vehicles in adjacent lanes. So essentially I get 7 feet left to place my vehicles. And I'm going to run just one vehicle here, the HL93 Tandem. And again, that's just in the interest of time. And the other thing I'm defining here is the analysis step. So how far do I want to move the vehicle in each increment? And that's my decision. I could choose to take very large steps and the analysis will go pretty quickly. I could take pretty small steps and the analysis will take quite a long time. But the difference is going to be the resolution on my load envelope. And in this example, I'm going to go in relatively large steps just so the analysis runs fairly quickly. And that's it. That's all the inputs I need to define the analysis of this structure. So there's a few new lines at the end. These are inputs needed for rating, so like a load factor, impact factor, multiple presence factor, fee factor, that kind of thing. But that's it. This is the entire input file. So at this point, I want to basically show how this input file then gets used in an automation routine. So Lubin, if you could jump over to the screen recording. So what I'm going to show here is a recording of my screen that I did. This was a week or two ago. And you should all be seeing Lubin's screen now. He's going to play the presentation. But what we're going to see is on the left, it'll be a Windows Explorer menu. And on the right will be a command prompt. So the automation routine I developed, it's written in Python, and it's what's called a CLI, or a command line interface. And that Python code manipulates and accesses the features of the commercial FEA program called Strand 7. Or on the left, and my automation routine, the command line on the right. I refer to it as BridgeMizer. That's just the name I gave to my automation routine. And what I'm going to do is basically pass in the Excel file that we just developed as my input file. It's my set of instructions. And what the code has just done is taken those instructions and built the analysis model. So initially, I don't want to do the entire rating. I just want to build the model. So that's what we're looking at here. The model is built. All my components are now defined as elements. The little black lines are links connecting the girders to the deck. And I basically can confirm that the model built exactly what I wanted it to do. So if you allow me a quick tangent, I'm going to go into my input file, the text version this time, not the Excel version, and make 2 quick changes. So like I said before, this process is now parametric. So the changes I made are I added a skew to the bridge, and I changed the way I want to represent the girders. So I made 2 quick changes, and I resubmitted that input file into the BridgeMizer routine. And as a result, it will then generate a new model. So the new model is going to represent girders with beam elements for the flanges and shell elements for the web. You see it did some internal checks there and gave me some information about my model. But now I'm going to open up the rendering again, and I can see the new model is now skewed. So the mesh is totally different, elements are totally different, and the connectivity is totally different, but it's the same structure. All I did was add add a skew and change the way I'm representing the girders. So that's what I mean when the model is now parametric. So in order to build this model by hand, it's a significant undertaking. But once you have the input developed, modifying it to make a slightly different analysis is really not a problem at all. So now I'm going to go back to my original model, the one without the skew, and I'm going to submit the entire analysis. So I want to build the model, I want to run my dead loads, I want to run my live loads, extract results, and compute ratings. And as I mentioned before, I was able to include some self-checking into the process. And one self-check procedure that I always do is running a modal analysis. So you see here on the right in the command line, as it steps through the process, it basically gives a printout of what it's currently doing. So after running the linear static analyses, it'll run a modal analysis, and then I'll open up that same viewer window again to allow me to view my modal analysis. It'll show me my mode shapes, and I can basically confirm that there's no errors in connectivity, that my properties are reasonable, and the mode shapes are reasonable. So in the background now, the automation routine is continuing to run. It's running the live loads. It's going to start extracting results. But while that's running, we're going to look at the mode shapes here. So I can turn on my first mode, and what I'm visualizing here is the shape of the deck, and that's a torsional mode that to me looks reasonable for this type of a structure. It's showing me that I don't have any errors in connectivity in the model. And here's my second mode, your first bending mode, and again, that looks reasonable. So I was able to quickly incorporate these self-checks. So the analysis routine has continued in the background. We see the live load cases have finished. There were 4 of them, 2 for the uniform lane load and 2 for the actual tandem vehicle. The next step was identifying composite sections, so which deck shell elements are within the effective flange length of each girder beam element. Once those are defined, then I can use all of those elements to extract composite demands. I output files that summarize demands and capacity calcs, and I could produce a load rating. So there we're seeing a short summary of the load rating, and the final step is I'm producing another plot that summarizes the rating and the conclusions. So the plot I'm bringing up now is basically a version of a summary table, but instead of just showing one output, I'm showing all output locations. So I'm kind of mixing vertical scales here. The colored plot is a rating factor. So we can see our moment is governed by rating at midspan, which we knew. But because of the cover plate, we can see the step there in the capacity and in the rating factor. So like I said, I'm mixing vertical scales. The gray line is a capacity and the other colored lines are demands. And then the contoured line is my rating factor. But through this type of integrated display of demands, capacities, and rating factor, I think you really get a more holistic view of the structure, how one region compares to another. So I'll pick up here with the conclusions from that demo. And what we see if we look at the refined analysis conclusions compared to the approximate method or the single line girder results from AASHTO and BE, there's a different dead load. And that's just a result of a different assumption about dead load in the 2 analysis approaches. We see more dead load in the exterior girder in the refined analysis because in the single line approach, it was kind of smeared through all the girders. We see a lower live load in both girders, and that's the result of the refined analysis approach. It's a more accurate representation of the live load than you get from the distribution factors in AASHTO. And as a result, you see better load ratings in both girders. But the real takeaway here is that we were able to do that refined analysis in 20 minutes. I think building that input file in Excel is not that big of a process. It's not that much longer than needed for a single line input, especially when you consider that you would need to do one for the interior girders and one for the exterior girders. So now that we have our refined analysis, what do we do with it? So at the end of the description of refined analysis in MBE, there's a line that says that a refined analysis should be used to produce distribution factors, which then makes additional load ratings easier, but it doesn't really give you any description as how to do that. And I've seen 2 approaches. So on the left, I'm showing an approach where your distribution factor is really computed using the full cross-section result. So in each case, you want to define a distribution factor as the individual girder live load divided by the entire live load. And the problem here, or the question here, is really how to compute that entire live load. And one option is to take a cross-section across the entire bridge and compute the resultant in the same way you did for a single girder, basically using the element results to find a composite moment. But the problem here is that as soon as your bridge becomes skewed, the choice of the cross-section to take becomes a little bit more difficult. So I don't really like this approach. On the right, I'm showing a separate approach where you could essentially isolate a single girder from your model and run that as a line girder. So put your vehicle on that single girder. So if your bridge is simply supported as it was here, you don't even need a model for it. It's determinate. And you can determine your total vehicle, or the denominator for this distribution factor, using just that single girder example, or single girder analysis. So this is what I have added into the automation routine. And when I run a compute distribution factors for that example, this is what I see. It's essentially showing lower distribution factors for moment and shear in my interior girder. There's in the neighborhood of a 10% benefit. Exterior girders is less consistent, but interior girders, we see the benefit. So the one thing I want to mention here is that these distribution factors, these are not properties of the bridge. These are properties of the analysis. All of the analysis analysis decisions that were made are kind of baked into these factors. So things like how the girders are represented, how they're connected to the deck, where the vehicles were placed in the analysis. If you move the vehicles transversely or move them closer together or farther apart, that'll affect these factors. And they're also a function of the vehicle. So I ran this bridge for a suite of 20 different legal design vehicles. And what we see is a range in distribution factors. So for the two-lane interior girder shear distribution factor, it varies from 0.54 to 0.72 depending on your vehicle. That's a pretty substantial range. And for the moment distribution factor, you see slightly less range, 0.52 to 0.57. But still, my point here is that these factors are analysis output. They're not a property of the bridge, and they are totally dependent on the analysis. So I want to get to one last topic here, and this is the issue of checking. So when you automate the process, the purpose is not at all to remove the engineer. It's really to make better use of their time. So the responsibility on the person doing the analysis is still there to do their self-checking. But those self-checking tasks could be made easier by the automation routine. Things like reporting element quality, so like aspect ratio of your shell elements, reporting your modal analysis results, being able to really quickly run a mesh sensitivity. I didn't do it there, but one of the inputs into this process was mesh size. I could have very quickly changed the mesh size and rerun the entire analysis and determined if my results are sensitive to the mesh. In the analysis, I could have the routine sum my dead loads and be able to compare to a separate dead load check to make sure I'm accounting for all the components. I can have it sum the live loads to make sure that my vehicle definitions are correct. The process has become traceable to the point where I can output all of the intermediate results. And that's what I want to talk about in the load ratings. So when I'm automating a load rating calculation, what I want to see basically is being able to trace the process from input to output. So I'm printing out, I didn't open all the files there, but I'm printing out quite a few different text files that just present results to allow me to go back and check the entire process. What I'm saying here is that I'm going to do the same checks no matter how the rating was performed, but the automation can help it. And once I'm done with my self-checking, it gets passed on to a QA or an independent reviewer. Their checks are going to be totally independent of the rating methodology used. So just because an automated routine was used to run the load rating, they're still going to do the same checks they would if it was a manual process. So speaking personally, when I'm asked to check something, I don't look at their another engineer's input file. I look at the bridge descriptions, the drawings, the inspection reports. I look at the model and the results, and that's what I'm doing. It's independent of the method that's used by the preparer to compute the load rating. So to sum up, I think the barriers to performing refined ratings are really diminishing, and it's becoming easier and easier to automate either a part of the refined rating process or the entire process. And the inputs for a multi-girder bridge don't have to be that much more difficult than the inputs required for most single-line girder programs. So yeah, the bridges I'm showing here, they're substantially more complex and the inputs are longer, but they're still much, much easier than doing a refined analysis through a manual approach of building these models by clicking through a user interface. And the engineer still retains all of the control on all of the decisions. So it's really condensing the engineering effort and rather distributing it through the process of clicking through a user interface. It's all put at the beginning and into an input file, which is then run by the program, and most of the time is spent in computer time as opposed to man hours. So once you have this output, the same checks are still required. So this tool doesn't get you around any engineering judgment or any understanding of the process. That's still all required, but it really enables a much better use of the engineer's time. So with that, I'll take any questions.
Thanks very much, Tom. 3 excellent presentations. I know Joe and Ben had to leave, but I think John is on the line with us and Tom is here. So if you'd like to ask questions of them, anything in the chat pod, I'll try to get those questions to Tom and John. Tom, let's see. Mr. Patel asked which software being used for preparing the model?
So I kind of spoke in generalities because I don't want to be partial to any one FEA program or another, but I've defined my model just as components. And then the automation routine takes care of breaking those components into nodes and elements. So once I have the nodes and the elements and the connectivity, I could basically put that into any FEA program I want. So that demo I showed uses a program called Strand 7, but it's basically just restructuring your text input to put it into a different program. I could easily have put it into SAP or ANSYS. It's just a matter of knowing the syntax of the inputs for those programs. So I think to answer your question is the model is built kind of outside of an FEA program. But that, it's certainly not the only way to do it. I didn't focus on building the model because I think FEA programs, the commercially available ones, have a lot of tools out there to build a model. And I'm not saying that you need to build it on your own, but just there are ways to improve on the standard process.
Thanks, Tom. And then Elizabeth asks, is BridgeMiser an input tool? Is it considered an input tool? And is it compatible with all FE programs?
It's certainly not compatible with all FE programs, no. I'm kind of working currently on expanding functionality to other programs because I know some state DOTs just specify which programs are approved and which aren't. Not on all state DOTs, but as I said, right now it works with Strand 7. I'm currently working on functionality to incorporate SAP, but I guess you can think of it like an input tool. It develops the input, but it also interacts with the solver by requesting analyses to be performed and pulling out results and then post-processing those results as well.
Thank you. And then David Warner, I think this is to your presentation, any experience with megaload, superload movements?
Yes. So this process could totally be used for a one-off style analysis. And I guess this might be a bit of a vision here for me, but if the input is already developed for a bridge, being able to quickly analyze an additional vehicle is basically just the effort of defining the vehicle. So we've used this process for permit analyses in the past, yeah.
Super. And then what was the program built on MATLAB or VBA or any other language was used?
So this uses Python. It's an open source programming language similar to MATLAB or VBA.
Okay. All right. I appreciate it. I would like to mention to everybody that this webinar number 23 pre-pack, the PDF there, is downloadable at this time, so you can upload that file. Somebody had asked earlier if all of these presentations are available. We've had 3 excellent presentations, and the email addresses of those that have made presentations are included in that packet. So I'm certain that they would be more than happy to answer questions or get feedback regarding their presentations. And really appreciate that. I see a few more people are typing, and let's see. David asked the question, experience or future use. Where are you going to go with this in the future? I guess you really mentioned that already, Tom, but any other thoughts on how to use this tool in the future or how to use the automation in the future?
I kind of see it as something that could be deployed like in a big picture sense, like having a library of input files for multiple bridges kind of along a corridor or maybe owned by a turnpike or a DOT, something like that. Doing it in a one-off situation is totally doable. It seems like it has a bigger implication.
For more information about automated refined load ratings for Girder Bridges or BridgeMiser, please contact Tom Golecki or visit our website at bridgemiser.com.